All right, I just wanted to give a little update on what's been happening in the world of direct conversion receivers here at N2CQR. We've been doing a lot of this area, been having fun. It's it's kind of surprising, as I said before, to go back to direct conversion receivers after having built so many SSB transceivers. It seems like a step backwards, but actually, I think, and many people have pointed this out, there's a lot to learn from direct conversion receivers and a lot of interesting kind of circuitry and technology involved here. The other thing that's going on is that inspired by Farhan in Hyderabad, we're Dean KK4 DAS and the Vienna Wireless Society and I are working on a project to help some high school students build their own direct conversion receivers. And we think that the direct conversion receiver is a good kind of entryway into the world of homebrewing radio, or at least getting familiar and getting some firsthand experience with building something technological. The Michigan Mighty Mite is a good step, but it's not really enough, especially not for kids who are more interested in the technology. I think the direct conversion receiver is a good kind of achievable objective that you could take on, and that you could end up with something that's really interesting. Not only that, it'll allow you to cross the threshold into the world of those who have built receivers versus those who have never built a receiver. And a direct conversion receiver is a real receiver, as you'll see. You might be able to hear it. I have the CW from this thing playing in the background here a little bit. I'm running it through a little amplified speaker, but this is basically what you'd hear if you were using, earbud headphones, the same thing. So it's not really cheating. I don't think. Anyway, we were starting to use the big amplified speakers because I was over at the school yesterday, and I needed something that was loud enough to fill up a fairly big room full of teenagers, so that they could clearly hear what was going on. My little amplified computer speaker wasn't quite enough, so I've moved up to a guitar amp, which is what we have plugged in here now, and that's what you're listening to. All right, let me just review what we have here. I'm pleased that we have basically 4 boards, and these are the 4 subcircuits of the DC receiver that we're going to work with the students to have them build their own, and that I've been just experimenting with and thinking about how best to do them and how to interface them and everything else. I'm going to move this one little wire here out of the way. That's just it's a wire that's powering things up there. Get that out of the way. All right. So the four boards are, well, you have the signal coming in from the antenna here. And the first board is a bandpass filter. It's a simple dual tune circuit, 2 tune circuits linked together by a 10 picofarad cap. Both of the tune circuits are tank circuits at the operating frequency for the 40 meter band. And I have these little trimmer caps in there, so it's easy to tweak this thing up and get it peaked up for 40 meters. We just took this off Hans Sommer's website, the circuitry, and just applied it directly, and there was no problem at all. G0 UPL at QRP Labs, his website has a lot of great stuff, including the schematics for the bandpass filters that Hans has available through the sites of QRP Labs. Now, right next to that, going right into it, boom, right here we have a diode ring mixer. There's the diode ring. There are the 2 tri-filler transformers on either side. Now, we played around a little bit about what ports to use and what best ports to use to come up with the right kind of signal. And this reflects what we think is the best way to do it. You have the VFO coming in here. You have the RF signal coming in here. And then over here, at this point, you have the audio coming out. And I built a simple Diplexer or Diplexer. This is the output circuit. The purpose of this circuit really is to make sure that all of the signals that you are that are coming out of the mixer, and there'll be many signals, not just the difference frequency that you want, but lots of other different signals will be coming out, and they all need to be terminated. They all need to be to find a suitable load, a 50 ohm load, or else they're going to be reflected back into the mixer and cause all kinds of trouble. Now, these Diplexer circuits, they vary a lot in complexity and difficulty. I was looking for something that was had a good reputation and that was fairly simple, and I found it, I think, in this very famous article by W7EL, Roy Llewellyn. He wrote about the optimized QRP transceiver for 7 megahertz. There it is. You can see it there. I'm sorry I'm holding it kind of sideways. It's just the way I have the camera set up. But this is really an important article. It was in the 1993 ARRL handbook. And inside this little transceiver is a direct conversion receiver. And he has the diode ring mixer, just like we do. I'll try to get this in front of the camera here so you can see what I'm talking about. We're not very high tech here today. Look, here's the diode ring mixer. There's the 2 trifilar transformers. And this circuitry here is the Diplexer or Diplexer that he uses. It's got a 0.01 microfarad capped ground and a 50 ohm resistor. This means that any RF, any high frequency RF coming through here, boom, it's going to go through here. It's going to find that path to ground. Then there's a low pass filter here that only passes audio. So any RF that remains here is going to be cut off by the low pass filter, and then it goes into the audio amplifiers. So this is really just 1, 2, 3, 4 components, and I built that and put it in here. And I hope one of the reasons to do this is that I hope this will help deal with the Radio Marti problem. Radio Marti it's not fired up now, but in a few hours it will fire up on 7335 with 250 kilowatts down there in Greenville, North Carolina. And if this Diplexer helps prevent any of the RF from getting to the audio port on this diode ring mixer, that might be an effective way, or it might help reduce the background QRM from the background interference from Radio Marti. Then the other stage that we have here, I guess is the third stage we're talking about. This is the audio amplifier. This is really a simple 2-stage audio amplifier with just two M3904 transistors. There's nothing fancy here. There's no feedback network. There's no negative feedback. It's very simple. It's a circuit that appears in one of the Forrest Mims books, one of those little engineering handbooks that he puts out. It's also very similar to the audio amplifier in the Hearing Aid 5 DC receiver that I unsuccessfully built as a teenager and successfully built 38 years later. One of the key elements of this is the output transformer. You can see it here. And I happen to have one of these in the junk box, probably from earlier attempts. You used to be able to get them in a blister pack from Radio Shack, but those days are gone. So I had this in the junk box and I used it and it worked fine. We went out and we bought some additional ones from Amazon, and they claimed to be the same thing that we needed. And what the circuit called for was a 1,000 to 8 impedance transformation. In other words, if you hung an 8 ohm speaker off the end here, which we do, it would appear as a 1,000 ohm impedance in the collector circuit of the AF amplifier. But we saw, and you'll see them a lot, these little transformers. They're being sold on Amazon and in other places, and they're said to be 1,300 to 8 ohms. So in other words, 1,300, you hang 1,300 off the secondary, and it appears less you hang 8 ohms off the secondary, appears as 1,300 here, which seemed to be just about what we needed. They were really cheap, so Amazon sent them to us, and I put them into the circuit. It worked, but it didn't seem to work as well as the older one. And I started to investigate it, looked into it a little bit more, and I went to the Amazon sites, and I found a very insightful comment, and it was from our old friend, Alan Yates. Alan was a very early participant in the solder smoke community, and he was the one who sent us the trivial electric motor and other circuits. So he's a guy who really knows which end of the soldering iron to grab. And he said he did some pretty extensive tests on these things, and it looked to him, and if I'm reading his comment correctly, they were not going to provide the 8 to 1,000 impedance transform. Rather, it looked to me like it was more like 8 to 200. So instead of putting a 1,000 ohm impedance on the collector of the audio amplifier, it was only going to put about 200 ohms. And sure enough, it worked, but it didn't seem to be amplifying as much. So I beat a hasty retreat, and I took this one out, and I put the old one back in. But all is not lost, because Mauser has, for real, 8 to 1,000 ohm transformers, and I bought a handful of them, and they'll be arriving this week. I was kind of worried about this one because I've used it so many times in so many circuits that the leads on it are like disappearing. It's terrible. I mean, look, here's another one I have. This one is even worse shape. Look at that. I mean, you could barely see the leads coming out of it anymore. They kind of over time get smaller and smaller, and then they're not there anymore. It's just very sad. But anyway, Mauser still has them, so I'm gonna get them, and I'll be prepared. Then we'll be prepared to build some more amplifier stages. But I like this little amplifier because it's very straightforward. It's not an IC. It's 2 little amplifier stages, and it seems to be very well behaved. It does not break into oscillation for me. It's fine. I really like it. Now, the other stage, and that's what we have up here, is the VFO. And you can see it's permeability tuned. It's using the same Hartley coil. It's a Hartley coil that Farhan used. This whole circuit basically is the same circuit, except changed for frequency, that Farhan developed for his Daylight Again transceiver. So I just built it. Dean KK4 DAS 3D printed the coil form, and I went ahead and built Farhan's Daylight Again VFO circuit, and then shifted the frequency. I think he built his for use at about 2 megahertz, and I just changed the capacitor values. You see the bank of capacitors down here, and got it up to 7 to 7.3 in that area, so we could listen to the 40 meter band. It's really stable. It works well with the screw, and one of my only problems with it was the screw seemed a little bit loose, and I didn't like that too much. So I put this little piece of wood here, a wood front panel, and I drilled a 1/4-inch hole, and it doesn't wiggle as much. It's much more solid. One of the downsides of this kind of arrangement is it's hard or almost impossible to come up with a kind of a completely analog frequency readout, because the frequency changes as you move the screw in and out of the PTO of the coil. So it's not like a variable capacitor where you could just draw your frequency range, as I often did. In this case, it's coming in and out, and it takes, I think, about 10 turns or so to cover the entire band. So even this little indicator that I have up here is not going to cut it, because the indicator is going to be going around and around and around. I read one article from about 1966 where the guy was looking for a place on the panel to put a mechanical turns counter so he could keep track of how many times he turned around with this thing. I even thought about, coming up with a very crude frequency readout by sort of painting onto this part of the screw, like the low portion of the 40-meter band, and then come out a little bit more. Okay, and there's the high portion of it like that, but that's kind of goofy. I don't know. We've got to solve this in a different way. But for now, it's a really good way to change frequency, especially if you're designing something that's going to be reproduced in some numbers. I mean, this is not the kind of thing where you could count on a junk box, because the students don't have any junk boxes. And variable capacitors are expensive now. Holy cow, eye-poppingly expensive. I went onto the internet today and even used stuff, even the old junk that shows up on a lot of the online websites, they're quite expensive. So Farhan is right. We have to look at different ways of changing the frequency, and this is a great way to do it with an analog circuit. Now, interesting questions came up, like, why are we using brass? Why would you use brass? Because, and this gets to the question, when you're moving the brass in, are you actually changing the permeability? Because brass has a permeability almost the same as air. So when you're moving this thing in, you're really just replacing air with brass, and you're not changing the permeability. However, the brass conducts, and anytime you put a conducting element inside here, it has the effect of serving as a shorted turn, a shorted secondary. So what that does is, in effect, it takes turns off of this thing. It takes turns off of the coil. It reduces the inductance, and if you reduce the inductance, you increase the frequency of the device. So as you screw this thing in, you're increasing the frequency that's coming out of the VFO. So that's sure enough. So I mean, if you're down here's like around the CW portion of the band. Let's listen. Here's some CW. We're in the CW portion of the band. Wow, a lot of CW. Now we're going to come up. Wait, there's FT8. Go up a little further. All right. We're increasing the frequency. See what I mean? So that's what brass does. Now, somebody said, Mike Danhart asked me at a radio club meeting, why don't you use steel? And I tried it. I have a steel screw. I think it was this one that I used, right? And you put the steel screw in there, and steel's different because steel is a ferrous material, right? It's also conducting. So when you put the steel screw in there, it has the effect of moving ferrous material in there. Now, when you put ferrous material in there, ferrous material has a tendency of increasing the inductance of the coil. If you increase the inductance of the coil, you're going to be dropping the frequency. So if this was ferrous material, you'd be screwing it in, and the frequency would not be going up, it'd be going down. However, a complication, it's also a conducting material. So you're introducing ferrous material, which has a tendency to put the frequency down, but you're also introducing a conductor, which has a tendency to serve as a shorted secondary and bring the frequency up. Bottom line is, you get both effects when you're using a steel screw as opposed to a brass screw. And as expected, we see that when you screw the steel screw in, the most important effect is the conductive effect, and it's counteracted a little bit by the introduction of ferrous material. So I found that when I used the steel screw, frequency changed, but like not as much. I mean, for example, with the brass screw, if I turned it once, it would turn maybe, say, 20 kilocycles. With a steel screw, if I turned it once, it'd turn like 14 kilocycles, because you've got two different kind of opposing actions, two different bits of physics at work when you put steel, a ferrous material, that is also conducting in there. And the interesting thing was I took a coil and I took a ferrite rod, like an antenna rod, that doesn't conduct. It's not conducting. It's just ferrous material. And when you put that in there, it really increased the inductance of the coil and really dropped the frequency down without any counteracting conductive effect to pull the frequency back up. So that's kind of we were joking that perhaps with these PTOs you'd have hams with like available at the input various screws that would give you different different rates of frequency change, and they could be maybe hanging off the front panel of the transceiver. I know this seems quite barbaric to the SI 5351 guys, but we were talking about that. Yeah, so that's the PTO. You know, I've taken a break for now because the other way to do the PTO is with the glue sticks. We've been talking a bit about the glue sticks. I'm looking around here for my particular glue stick. Anyway, we have a lot of different. Here it is. Look, and Nick M0 NTV. I jokingly told Dale Parfit that we were turning this matter over to Nick, who's been appointed to the new glue stick permeability tuned oscillator research institute. But this is an interesting way to do the same thing that we're doing here, just moving this in and out. And what's moving here is you're moving, I think I mentioned this in a previous video, here I'm just moving a core. I'm moving a bit of type 6 material into the core, and that changes the frequency. Now, I liked it, but the one thing I found, and people have noted this, is that these kind of devices, they're so simple, there's a little bit of play, so that when you're turning it, it's okay. But when you change directions, there's a bit of sloppiness in there because the screw isn't engaging on the other direction yet. So some people have proposed putting a spring that would hold basically the cup, that part that moves, down onto one side of the screw thread. But, well, I don't know. That just seems like kind of a very painful solution to me. This is supposed to be simple, so I haven't tried it, but we'll see. There may be that there are other stick-like devices like this that have better screws. I know that there's a whole variety of glue sticks, chapsticks, lipsticks, all these kind of things. Hey, speaking of screws, one thing that I was thinking about, you know, this is a 1/4-inch brass bolt, and you know there are different types of thread. This is what's known as coarse thread or type 20 thread, but you could get finer thread where it's actually just a lot more turns, fine thread, and that's type 28 thread. Again, a 1/4-inch brass bolt, but with coarse thread. So I've ordered those. They're not really as available as this kind of coarse thread, but I'm thinking that might be a little bit smoother turning. It might hold in there a little bit better. I'm not quite crazy about the wobbliness of this arrangement right now. Another solution that came up, and this was kind of interesting. My friend Dean, KK4DAS, recommended using some plumber's tape and putting some plumber's sealing tape, some Teflon tape, in there on the threads, and then screwing it into the nut. And here's the tape. He gave me a bunch of it, and he said it made for smoother turning, and that would help out. But he right away predicted that it would also cause trouble because there's a feature of the circuit here that I put in that I think is really useful. You see this little wire here? Let me get a light and put a light on it. You can't see it too well here now, but Put my light there. Now, in there, you can see it right in here. I have a bit of solder wick, and it's just going from ground on the board into the nut, into this plastic thing and the nut sits on top of it. And that in effect grounds the entire brass nut and bolt mechanism. And what that does is it gets rid of the hand capacitance effect. Before I did this, every time I grabbed the knob, the frequency would change like crazy, which was quite annoying. But once I grounded it, boom, the hand capacitance effect is gone, and I don't really have to worry about it at all. However, it prevented me from using this tape because the tape, in essence, insulated the screw from the nut. The nut was the only thing that I could really ground. And when I put this on, sure enough, my ingenious, grounding solution to the hand capacitance problem was negated. so I couldn't use that. But so we'll stick with that. I think right now stick with this kind of grounding arrangement, and maybe the number 28 screw will help a bit. But hey, let's listen a little bit. I've got this thing hooked up to the big. It's a big guitar amp, so it's more cheating even than the. Oh, that's one thing I want to talk about here before we get to that. I tried to measure how much audio gain this thing produces. It's kind of hard for me to measure audio gain, but the best I could come up with, my best estimate was that these two stages together were providing about 49 dB of gain. Now, I had always been taught that a real receiver needed 100 dB of gain. But when I put the headphones in with this thing and listen, I can hear down to the band noise, all right? So more gain really isn't going to get me that much. I can hear weak signals. When I put the HP 8640 into this thing and try to hear what is the lowest level signal I can hear with the headphones, I can hear down to about negative 110 dBm. All right. I know sometimes receivers go down to 130, 140 dBm, but they're looking at, I think usually the bandwidth is at CW bandwidth. This is quite wide. This is really maybe 6 kcs wide, 3 kcs on either side of the zero beat. So it's quite wide. So I think negative 110 might not be bad for this receiver. So I wonder what you guys think about that. And I've been kind of surprised because the only gain, there are only 2 powered stages in this, as you can see from the little blue wires. The only 2 powered stages are the VFO stage and the AF amplifier stage. The only active gain here is the 49 dB from the audio amplifier. There's loss in the filter here, there's loss in the mixer. But even with, 40 dB or 39 dB of gain with the headphones on, I have no problem at all listening. But it's been surprising to me because I kind of grew up with the idea that you need 100 dB of gain. Even in Roy Llewellyn's article, they talk about having 100 dB of audio gain in the receiver. Here's another thing interesting I want to point out. Let me talk about this a little bit here. When you read about DC receivers and recommendations for it, they always tell you that you have to have the VFO in its own sealed box, right? To keep the VFO energy right where you want it. But I built a lot of DC receivers, and I've never really gone to the trouble of putting it in its own separate box. And I usually haven't had a problem, okay? Now, maybe I have problems and I haven't noticed them. But one thing I was looking at, now the article by Roy Llewellyn, W7EL, is really, it's a famous article and people will refer to it all the time. It's a really great article on how to do a DC receiver. But take a look at that thing. How much VFO isolation do you think he could have in that tiny little box? Look at it. There's a quarter right next to it, okay? Look at the inside. He's got a picture of the inside. And this receiver, obviously, this transceiver, obviously works great. But again, here's the picture. Look, I mean, there's not a lot of shielding of the VFO in there, and it works terrific. So I don't know. I'm taking this kind of this admonition that you need it to be shielded with a grain of salt. I suspect that we could put this thing in its own box, and that we wouldn't notice any difference. It would just cause a lot of additional work. One thing I might do is I might just put some shielding up around here on this side and this side, and then have, without actually sealing it all up, but see how it works. It works that way. All right, so let's listen a little bit. The New York QSO party's underway. It's Saturday, the 15th of October, about 5 p.m.
You're right. You're 5-9 in the state of Virginia. Victor Alpha, QSO. We had 5-9 Oakley. I'll turn the other towards it. I gotta buy it for a price. As if it's broken, I know I'm worth it. Or I ain't gonna buy it. You know, everything I buy at a price that. I-9 and Otsego, Oscar Tango Sierra, over.
Get up to the top portion of the 40-meter phone band here. There's the AM at around 7295.
So a little bit off of where we're at, but that's.
Again, AM doesn't sound really great in a DC receiver, but you can listen to it a little bit.
That's what I got him on, so I went and put the transmitter and tuned up for it where he was transmitting. So anyway,
this is in essence the problem of listening to a double sideband signal on a DC receiver. There's all kinds of problems and distortion. Distortion that you won't get when you listen to an SSB signal. But it's still, you can still hear it.
You can easily correct. I mean, if you have the know-how ability to do that, but they're not, real new where they're real small surface mount, but in surface mount components, and there was these little flat packs in there. Resistor packs or whatever. I think I had to resaw.
Well, let's go down to the CW portion. You can see how many turns they have to do. SFT8. Into JPR. And looking for calls in the QSO party. As you can see, it's a really effective receiver for 4 little stages on 4 boards. And I got to say, the students that we were working with yesterday were really fascinated by the whole thing. I had a very suboptimal antenna, just 50 feet of wire thrown out the window there in their school lab. And I didn't have a good amplifier here, but we were still pulling in CW signals and phone signals, and they were listening to the whole thing. And they were really quite interested in the whole setup. I mean, these are students who are at a school that focuses on science and technology. So they had a natural kind of affinity for this kind of thing. But I was really surprised by how deeply they were interested in it. And they were interested not only in the signals, not only in the ham conversations, but more fundamental questions like, where does the noise come from? And is the noise necessary? And what can we do about the noise? And what's the relationship between the signal and noise? We got into signal to noise ratio discussions, things like that. And they really liked it. They liked, I think, the whole thing. So I think we're going to have a good experience. We're going to work on building DC receivers, much like this one. I mean, some of the circuitry may change a little bit. We're coming up. We're shooting for simplicity, reproducibility, and educational value. So we're looking at. We don't want to build these things for them. We want the students to actually build it themselves and to the greatest extent possible participate in kind of the design of the 4 boards. This could be seen as a kind of a first step towards actually producing PC boards in the more traditional sense. But we'll probably use a combination, maybe on different boards. Maybe one will be Manhattan style, one will be dead bug, one will be the various forms of ugly construction, and maybe one board will then give them an opportunity to kind of use a CAD software and actually design a PC board that could be reproduced in kind of traditional PC board style. But anyway, that's what's been going on here. A lot of fun with DC receivers. It's really great to be able to reach out and talk to people like Wes Hayward, who was really the one who launched the DC receiver revolution in the age of the transistor with his November 1968 article. It's also great to be able to talk to Farhan about this, who's involved in a kind of a similar effort and comes up with a lot of the ideas, similar effort to use the DC receiver in schools. Hey, one of the things we were talking about, I wanted to mention this, when we do build it with the students, the question is, which board would you build first? And Dean and I were talking about that this morning, and I think Dean agrees, the first board we should have them build should be the oscillator board to get it oscillating, because that would give them the same experience that many of us got with the Michigan Mighty Mite. You will have built something that produces RF energy. And even without having the rest of the receiver built, on a commercial receiver or on an oscilloscope, and they have oscilloscopes in their lab, you could see that the device you built is producing RF at 7.3 megahertz. So that would be a good kind of way to kick this off. Have everybody build the oscillator first, and then move on to do the other stages. So the mixer is obviously the heart of the whole thing, and the mixer there'll be some discussion of how the mixer does its thing. I don't know if we'll do the diode ring, or we'll probably go with something simpler, maybe 2-diode mixer, something like that. But just a little bit. The mixer is good because the students have received quite a bit of math, and it's an opportunity for them to see their math, Fourier transforms and things like that, in practice being used to receive actual radio signals. So when I showed them the radio yesterday, they even were fascinated by CW. And the fact that they could hear the Morse code coming through, and when I disconnected the antenna, it all disappeared. It was great fun. So we're having a lot of fun with DC receivers, and that's the latest from Solder Smoke headquarters. Put comments down below. Subscribe to the videos if you like them, and like I said, put comments down below. And I always take a look at the comments, and I really appreciate the input and the interest. For now, 7-3 from Northern Virginia.